Ever stop to think about what would happen if a single router failure could split your company's entire network in two? Or what if one critical intersection shutdown could gridlock a whole city? Well, today we're diving into exactly that, how to find those single points of failure before they cause a disaster. So, what is your network's breaking point? And this isn't just some theoretical question, you know? Figuring out these vulnerabilities is absolutely critical if you want to build resilient systems. And it doesn't matter if we're talking about computer networks, road systems, or even the dependencies in your software. Okay, so first up, let's talk about the articulation point. You'll also hear it called a cut vertex. Just think of it like a critical intersection or a central hub. If you take this one node out, the whole network shatters into disconnected pieces. It really is the linchpin holding everything together. And then you've got its counterpart, the bridge, or cut edge. Now, this isn't a node, it's a single connection. It's that one lonely road between two towns, or that single cable connecting two server racks. You snip this edge and the network splits right in two. It's the only path. All right, so now we know what these weak links are called, but let's dig into why finding them is so incredibly important in the real world. And believe me, the applications are everywhere. In a communication network, an articulation point could be that one critical router everyone depends on. For a road system, it's that major intersection that, if it closes, just gridlocks the entire city. In software, it's that one little module that brings the whole system crashing down when it fails. And yeah, even in social networks, it's that one person who connects two totally separate communities. Now for the brilliant part, how do we find these weak links without testing every single node and edge one by one? We use a super clever approach based on a depth-first search, and I absolutely love this analogy for it. We're going to explore the network using safety ropes. So picture this. Our depth-first search is crawling through the network, and as it explores, it's basically building a tree structure. As we go deeper, we create new branches. But every now and then, we find a connection that leads back to a node we've already visited higher up in the tree. That's a back edge, and that, my friends, is our safety rope. It's an alternate path backup that gives us that crucial redundancy. Now, to make all this work, we just need to track two key numbers for every node. First is the discovery time. We'll call it disk U, which is basically just a timestamp for when we first arrive at a node. Simple. But second, and this is the magic part, is the low link value, or low U. This just keeps track of the absolute highest node in the tree that you or any of its kids can get back to using just one of those safety ropes. So with our safety rope analogy and these two little measurements in hand, we can now define three simple but incredibly powerful tests to find every single weak link in our network. Okay, looking at this table, the real key is the subtle difference in these conditions. For an edge between parent U and child V to be a bridge, the child's low link value has to be strictly greater than the parent's discovery time. That means its entire branch has no safety rope that can even get back to its parent. For the parent to be an articulation point, the child just needs to be unable to climb strictly above its parent. It might be able to get back to the parent, but no higher. And then there's a special case. If the root of our search has two or more children, boom, it's automatically an articulation point. I'm going to say it again because this is so important. This tiny difference between greater than for bridges and greater than or equal to for articulation points, that's the whole ballgame. It's a classic interview question, but that climbing above analogy should really help it stick. Can you get strictly above me? No? Then I am a critical point of failure. But honestly, the best part of this whole approach, which was developed by the legendary computer scientist Robert Tarjan, isn't just how clever it is, it's how unbelievably efficient it is. This algorithm runs in O of V plus E time, which is just a fancy way of saying it's in linear time. What that means is the runtime scales perfectly with the size of the graph, the number of vertices, V, plus the number of edges, E. No matter how big and messy your network gets, if you double its size, you just roughly double the work. For this kind of problem, you literally can't get any faster. And here's why it's so fast. We don't have to constantly rescan the graph or do any crazy calculations. Everything, calculating discovery times, low link values, checking all our conditions, it all happens during one single trip through the graph. One pass, and we've got all our answers. It's beautiful. So let's bring it all home. How does all this translate into practical, real-world solutions? Well, finding these weak points is step one. The next step is using that knowledge to build much more robust systems. So here's your cheat sheet. If you're in an interview, first thing to say is that this works on undirected graphs. Be ready to recite those three conditions perfectly, and don't forget to mention the linear time complexity. And in practice, the game plan is clear. You find an articulation point, you add some redundancy around it. You find a bridge, you add a parallel connection. This algorithm literally gives you a roadmap for hardening your systems.
And that leaves us with one last thought to chew on. In all the complex systems you work with every day, whether it's code or infrastructure or even how your team communicates, which invisible bridge is holding it all together? Because finding it before it fails, well, that's what separates a robust system from a fragile one.